Good afternoon. The next topic that we will be studying is set operations. So in the last class, if you remember, we have studied sets. So what do you mean by sets? Sets are unordered collection of objects. Now for those sets, what are the different types of operations that can be done? So whether can they be combined, or whether can we find the common elements of two sets, and so on. So in this way, let's begin the topic set operations. So whenever we have two or more sets, they can be combined in different ways. So combination of different sets, combining two or more sets in different ways, or else finding common elements, or finding the complement, etc. So example can be, suppose if you have a department of computer science engineering students and a department of IT, information technology students. So you have a department of CSE students, and similarly you have a department of IT students. What are the total number of students in department of CSE and IT needs to be found for some seminar. So in this case, what you are supposed to do is combine the department of CSE and IT students. So this can be considered as set C, and this can be considered as set I. So both of those departments need to be combined, and we need to find the combination of these two departments. Similarly, if we want to find if both of the departments have a subject of artificial intelligence, and a few of the students from CSE and few of the students from IT are taking the same subject, artificial intelligence. Now what we can do is, if we want to find the number of students taking artificial intelligence from both the departments, this is another operation that can be done in sets. So let's begin with set operations. The first operation that we are going to study is union. If A and B are two sets, the union of the two sets A and B is denoted by A union B, okay? And it is the set that contains those elements that are either in A or in B or in both. So let's see an example. If you have a set A as A is equal to 1, 3, 5, this is the set A, and B is 1, 2, 3. Now, for the union is denoted by this symbol A union B. We need to take the elements that are either in A or in B or in both. So first, let's start with the elements which are in A and B. So first we have to write all the elements of A. So 1, 3, 5, and then all the elements of B. So 1 has been already written, so we don't need to write it 2 times. 2 is missing, so we can write 2 over here, then 3, and then 5 is in A. So this is the union of A union B. Okay. And then the next thing is, whenever, if you notice, 1 is in both A and B. Okay, 1 is in both A and B. 2 is in only B. 3 again is in A and B. 5 is only in A. So whenever we are taking the union, you have to remember that we have to take the elements of both A and B, and also which are simply only in A and which are only in B. And another way to express A union B in terms of connectives is, whenever we have A union B, it can be expressed in terms of connective in this way. So A union B is equal to, so whenever, if you remember, we are taking, in the case of set builder notation, A union B, we write X, there is an element X such that X belongs to A. Okay, element X is in A or element X is in B, belongs to B. What does this statement mean? If suppose X is in A, true, and X is in B, then it will be in A union B. If suppose X is only in A but not in B, even then it will be in A union B. Why? Because we are using the connective. The connective that we are using is OR. Okay, so the connective being used is OR. So if even one of them is true, it will be true. So let's see with the last case, last scenario. Last scenario will be the vice versa of true false, which is false true. Even then it will be true. If X is not in A, if X does not belong to A, and also or X does not belong to B, then X will not be in A union B. So this is the false, false, false case. If A is false, B is false, then A union B will also not have the element X. Okay. So the same thing. Let's see over here. An element X belongs to the union of the sets A and B if and only if X belongs to A or X belongs to B. And this tells us that we are using the connective OR. And if you remember, I have told you something about Venn diagrams in the last class. So what will be the Venn diagram of union? So the Venn diagram of union will be this. A union B. So over here, whenever you're talking about Venn diagram, if you are using union, then the shaded part will be the entire A union B. So entire, if this circle is denoting A and the other circle is denoting B, then you have to shade the entire A and B, both of the circles. Okay, this is A union B. Similarly, the next topic is intersection. So for intersection, again we are taking A and B as two sets, and the intersection will be denoted by inverted U, and it is the set containing the elements which are just in both A and B. So only the common elements of A and B are to be taken for intersection. Let's see an example. For this, suppose the intersection of the sets, same sets I am taking. So A is 135 and B is 123. Then the intersection will be the common elements. So let's circle the common elements. The common elements are 1. 1 is in both A and B. And then 3. 3 is also in A and B. So the intersection of A intersection B is 1, 3. Okay, this is the intersection. Now how can you represent it in the terms of connectives? So A intersection B can be represented as X such that X belongs to A, X belongs to B. Now if you think about it, the connective that is used for intersection is very obvious. That is, we will be using the connective AND. So if X should be both in A and B. If both of them are true, then only true. Otherwise, all the other cases will be false. So we will be using the connective AND for intersection. Okay. Now the next thing, let's see the Venn diagram, for Venn diagram, I'll draw it over here. So whenever we are drawing Venn diagram, we are supposed to take a universal set which is denoted by a rectangle that I've already told in the last class. And then for each of the sets, you are supposed to take a geometrical figure which is usually taken as a circle. So for both the sets, you will have to take a circle. So these are the circles. And now let's write what each of them denotes. So each of them, so this universal set will be denoted by U, and this is your set A, and this is set B. Then the next thing will be, we have to shade. So which region should we shade? So the region which should be shaded is the common part of A and B. So this is this part. It should not exceed that region which is common for A and B. Okay, so this is the Venn diagram for A intersection B. Now let's see the, so intersection, an element X belongs to the intersection of the sets A and B if and only if X belongs to A and X belongs to B. And A intersection B, we are using the connective and this is the Venn diagram, A intersection B. Next we will study a topic related to intersection, which is disjoint. Now, two sets are called disjoint if their intersection is the empty set. So basically what we are saying here is A intersection B should be empty set. If you remember, it was denoted by the symbol phi. Okay, so A intersection B should result in a phi. Then that kind of set is known as disjoint set. Okay, let's see an example for the same. So over here, two sets are taken. A can be 1, 3, 5, 7, 9. Odd numbers less than 10. Similarly, B is even numbers less than 10. 0, 2, 4, 6, 8, 10. Now, what is the intersection of these two sets? So if you want to find the intersection, is there any number which is both even and odd? No, there is no such number which is both even and odd. So in this case, A intersection B is an empty set. If you notice, 1 is in 1, 3, 5, 7, 9 is only in A. Any of those element is not in B. Okay, so for that reason, A intersection B is phi. Next, now whenever we are speaking about the counting the number of elements in the set, that is cardinality. Okay, cardinality of a union of two finite sets A and B. And what we do is we take the cardinality of A and then we take the cardinality of B. Now whenever we take cardinality of A plus cardinality of B, what it does is it counts the element in A, it counts the element in B. But what about the elements which are in both A and B? Those elements are being repeated twice in the case of counting. So let's see an example for that with the example that we were seeing earlier. So over here, if I take the same example 1, 3, 5 and B is 1, 2, 3, if we want to know the total number of elements in A union B. Okay, so in this case, the thing will be, if we want to count the total number of elements, one example will be directly finding A union B, which is 1, 2, 3, 5. Okay, cardinality of A union B is 4. But if you notice, there are 3 elements in A, 3 elements in B. So cardinality, if you just think about it, it should be 6. Why is it 4? The reason it is 4 is the elements which are being repeated twice, we should take them only once. Okay, so for that reason, the cardinality of A union B is 4. So the same thing can be shown by a formula, which is cardinality of A union B is written as cardinality of A plus B minus whatever is being repeated twice, we have to remove it once. So from here, we have to remove A intersection B once. So if you see, A intersection B was 1, 3. So cardinality of B is 3. Cardinality of A is 3. Cardinality of B is 3 minus, what is the cardinality of A intersection B? 2. So 6 minus 2, it is giving us the result 4. Okay. So this principle is known as principle of inclusion exclusion. This principle is known as principle of inclusion and exclusion. That is, we are including the elements which are only in A or in B once, and we are excluding the elements which are both in A and B once. Okay, so this principle is a very important technique which is used in enumeration, that is counting, and we will study this topic again in unit 3. Next. So the same thing, A union B is equal to A plus B minus A intersection B. And it is the principle of inclusion exclusion. Now, the next topic is difference. What do you mean by the term difference? So if A and B are two sets, the difference of A and B is denoted by A minus B. And it is the set that contains the elements that are in A but not in B. So difference of A and B is also called as complement of B with respect to A. Okay. And how are we denoting A difference? We are denoting it by using the negative symbol. Let's see an example. So the difference of the same sets, A is equal to 1, 3, 5. B is equal to 1, 2, 3. Now we are supposed to find A minus B. So in this case, it will be only the elements that are in A but not in B. So it can be shown in this way also. That is, we can write 1, 3, 5 and minus 1, 2, 3. Now to make it simple, what we can do is we can cancel the elements which are in both A and B. So one is in A and one is in B. Okay. Next, 3. 3 is in A, 3 is in B. Now 5. 5 is only in A. So the solution will be the element which is left over only in A. So this will be equivalent to A minus B is equal to 5. Now, what about B minus A? What is B minus A? So B minus A, you have to write it as 1, 2, 3 minus 1, 3, 5. Once again, let's cancel the elements which are in both A and B. So 1 is being cancelled. 3 again. 2 is the one which is only in B but not in A. So B minus A is equivalent to 2. So one more thing to be remembered is A minus B is not equal to B minus A. Next. The difference is also denoted by A slash B. And it is also known as by using the connective. An element X belongs to the difference of A and B if and only if X belongs to A and X does not belong to B. Okay. So by using the connective, we can write it by using and, that is X should be in A and X should not be in B. X does not belong to B. This is the Venn diagram, that is we are skipping the common elements. Let me write here. Skip the common elements. and all the elements of B are left, only the elements of A are taken, which is not in B. So this is difference. Now the next thing we will be studying is complement. So we studied complement of B with respect to A. Now we will be seeing the general complement definition. Now, what do you mean by complement? So complement always involves the universal set. If we want to find the complement of a set, we are supposed to take the universal set. And the complement is denoted by the complement of the set A is, this is simply A. So the complement of the set A is denoted by A bar. It is the complement of A with respect to U. It is the complement of A with respect to U. Therefore, the complement of the set A is U minus A. Okay. And it can be represented by, A bar is usually represented by, if X belongs to the universal set such that X should not belong to A. Okay. And the Venn diagram for the same is represented by shading the entire rectangle by leaving the circle. Okay. Let's see. An element belongs to A if and only if the element should not belongs to A bar. And the formula in terms of set builder notation is X should belongs to U, that is the universal set, but it should not belong to the set A. And let's see the Venn diagram. So you are shading the entire rectangle, that is the universal set, by leaving the circle which is your set A. Let's see an example. For the example, you always have to specify the universal set. So the universal set is to be specified. This is very, very important. Universal set has to be specified for finding the complement. And in this case, U is the set of all positive integers. Okay. And A is the set of positive integers greater than 10. Okay. So all the integers greater than 10, it belongs to the set A. Now we are supposed to find A complement. So for A complement, what will be A complement? From the universal set, we have to remove the entire set A. So the universal set is positive integers. We have to remove all the positive integers which are greater than 10. So in this case, complement of A will become set of all positive integers less than or equal to 10. So the solution for this will be A bar will be equivalent to all the numbers from 1 to 10. So this is the complement of the problem where A is the set of all positive integers greater than 10. Okay. So the next topic that we are supposed to study is set identities. So set identities are very similar to the laws that you have already studied in proposition. So set identities are a list of laws that we usually use in the case of solving problems for getting equivalent laws. So over here, even the laws are similar to the laws that you have already studied in propositional equivalence. Identity law. So identity law, while we studied identity law in logical equivalence, let's recap a bit. So the identity law for logical equivalence was P and T is equivalent to P. Also, the other pair was P or S is equivalent to P. So, identity law was that whenever you are using and or with true or false, then we will get the same proposition P. Similarly, over here, if we, in case of T, we are replacing this T in the case of sets with the universal set capital U. And we are replacing the false with the empty set phi. And is similar to intersection and or is similar to union. So if, in this case, if you notice, the identity law is A intersection universal set will be equivalent to A union empty set is also equivalent to A. So let's see an example. So if A is 1, 2, 3 and the universal set is 0, 1, 2, 3, 4, then A intersection the universal set is equivalent to A. So 1, 2, 3, what will be the union of these two? It will again result in the same thing 1, 2, 3. Okay. Similarly, A, if I am performing a union with the empty set, then again it will result in an A. Okay. The same way you can take examples for each of the law and you can perform union and intersection in such a way that you can prove the law. Okay, the domination law, it is again similar to the domination law that we have studied in logical equivalence. Idempotent law and complementation law is your double negation law. That is, we are applying complement 2 times, which will be equivalent to the set itself. The next is commutative law. Commutative law is similar to the commutative law of even mathematics. A plus B is equal to B plus A and so on. De Morgan's law is the one which is important. We will see an example on De Morgan's law. Yeah. So we are supposed to prove A intersection B whole complement is equivalent to A complement union B complement. Now for this, I'll start proving it first and then we can see the overall solution. Let's take the equivalence that we are supposed to prove. Let's start. We are supposed to prove that A intersection B is equivalent to A complement union B complement using set builder notation. So using set builder notation means we have to express it in the form X such that. So let's take our left hand side. A intersection B complement. How can we express it? We can express it in this way. X such that X does not belong. So whenever we have complement, you remember X, we are supposed to use X does not belong to A and B. A intersection B. Okay. So this is by the definition of, which definition you are using? By definition of complement. Okay. Now the next step, we have A intersection B. This can be replaced by the symbol and, so we will do that. X such that now does not belong, we can use the symbol negation. So over here, negation of X belongs to A intersection B. So for this, we are using the definition by definition of does not belong symbol. So does not belong symbol. For this, instead of does not belong, we can always use negation. After that, this is equivalent to, now A intersection B, this can be represented by using the connective and. So let's represent it by using the connective and. X belongs to A and X belongs to B. So this is by using the definition of intersection. By definition of intersection. After that, we are supposed to apply the De Morgan's law. So De Morgan's law is we are supposed to apply negation to the first variable, change the sign, and then apply negation to the second variable. So let's see that this negation is applied to the first variable, applied to the symbol, and then applied to the second variable. So this is equivalent to X such that now the entire thing can be written as negation of X belongs to A. The symbol and will change to or, negation of X belongs to B. This is by using De Morgan's law. For logical equivalences, we are using De Morgan's law. Okay, since we are using it on a connective, we are supposed to use the logical equivalence De Morgan's law. Next, again by the definition of does not belong symbol, over here we had does not belong, we used negation. Here we are doing the opposite case, that is the does not belong symbol will be changed, the negation will be changed to does not belong. So let's start. X such that X does not belongs to A or X does not belongs to B. Again, you are supposed to write the same thing over here by definition of does not belong symbol. Now, for the next step, the does not belong symbol earlier was complement at the beginning. So the same step is repeated again by definition of complement. X is such that X belongs to A complement or X belongs to B complement. Okay, so here we are supposed to write the rules, and this what I'm writing, the definition by definition of, this is very, very important. So first one was by definition of does not belong symbol, and the last is by definition of complement. Now if you notice, we have almost got our result. Now the only thing which is to be changed is the or symbol is to be changed to union. So this symbol is to be changed to union, and we are supposed to write it in the normal notation. So let's do that. So the last step, I'll erase the first part. The overall solution will be provided. So from here, I'm continuing on the top. So by the definition of complement, we changed it to X belongs to A bar and or X belongs to B bar. Now again, X belongs to A bar union B bar. This is by definition of union. Okay, so the last step was here union. So we are just replacing the or by union, and by using set builder notation, this will be equivalent to A bar union B bar or A complement union B complement. Now let's see the actual solution. Yeah, so over here the first step by definition of complement, we changed it to negation, and the same thing by definition of does not belong, then complement union, and the final solution. This is the overall solution for this proof. It is an important proof from the perspective of an examination. Next is another proof, which is let A, B, and C. So over here we have three sets. Show that A union B intersection C whole complement is equivalent to C complement union B complement intersection A complement. Okay, so this is simpler than the other proof. Let's prove it. So we have the equation A union B intersection C whole complement. Now we can simplify the complement directly. That is, we can write A. If you are applying complement to union, it will be changed to intersection, and then again we apply the complement to the entire bracket. After that, A complement intersection for B intersection C. Okay, this is intersection. For B intersections C, apply them to each of the sets individually and also change the intersection. So B complement union C complement. After that, over here I'm supposed to mention the law, so De Morgan's law. Okay, now one question is why we are not using the proof the way that we have used earlier. So in the earlier question, it was clearly mentioned that we were supposed to use De Morgan's law. We were supposed to use, set builder notation. Over here, it has not been mentioned, so we can use our set identities. So this is De Morgan's law. Again, the same thing, De Morgan's law. Now, after that, since we have it in the form of C union C complement union B complement, that is, the bracket is first, so we can use commutative law. Commutative law is basically rearranging. So B complement union C complement intersection A complement. Again, this was commutative law for intersection. Now we will be using the commutative law on the inner bracket, so it will be C complement union B complement intersection A complement. So this was what we were supposed to prove, and since it has not mentioned set builder notation, we used set identities. Okay, let's see the solution once. By the commutative law for unions, intersection, and the same thing. Now, if we have three sets, how are we supposed to draw the Venn diagram? These are the way. For A union B union C, we can make the three circles intersect and then we can shade it. This is for A union B union C. For intersection, we are supposed to only shade the part which is an intersection of all three of them. That is, over here all A, B and C intersect. So this is the shaded region. This is an example of Venn diagram. Maybe you will get this in 2 marks, but otherwise this is just for representation purposes. Now, there is a problem. Let A is equal to 0, 2, 4, 6, 8, B is equal to 0, 1, 2, 3, 4, and C is equal to 0, 3, 6, 9. What are A union B union C? For A union B union C, we are supposed to take all the elements of A, B, and C, and if few of them are being repeated twice, you're supposed to take only once. So 0, it is in all A, B, and C, so let's just write it once. Then let's look for 1. It is better to always have a set in some order, so let's look for 1. 1 is there. Then we have 2. What about 3? 3 is also there. 4. And then 5 is in none of the sets, so no. Then 6 is in the set C. 7 is also in 7 is not there in any of the sets, so let's move to 8, which is in A, and then 9, which is in C. So this is A union B union C. What about A intersection B intersection C? So which number is common for all three of them? So we have 0 in A, B, and C. So 1 can be 0. After that, what about 2? 2 is in A and B, but it is not in C. The same with all the other elements. So A intersection B intersection C is only 0. Okay, this is the solution. This is the solution. Next, the union of collection of sets is the set that contains those elements that are members of at least one set in the collection. So basically what we are saying is, if we want to take multiple sets such as A1, union A2, union and so on up to AN. So there are n sets that we are taking, then the union will be union of sets from 1 to n AI. Okay, so it is the union of all the sets. Similarly for intersection, it will be the intersection of all the sets. So we took an example with 2 sets and 3 sets, but for multiple sets you can have a formula in this way: intersection I is equal to 1 to n AI. Okay, now let's see an example. So let's see an example for sets and then sets operation, and then we will end the topic. So the example is A is equal to ABCD and B is equal to ACYZ. We are supposed to find A cross B. So A cross B is the Cartesian product. It will have how many elements? So if there are 4 elements in each of them, so we have to make a combination of all of those. So I'll just begin the solution. You can solve it for yourself. A comma A comma C, A comma Y, and then AZ. After that, similarly for B, BA, BC, BY, BZ, and then CA, CC, CY, CZ. After that, DA, DC, DY, DZ. Okay, so this is A cross B. Similarly, you can find B cross A. So B cross A, I'm leaving it as an exercise for you. The next is cardinality. What is the cardinality of A? How many elements are there in A? There are 4 elements. So the cardinality of A is 4. Similarly, the cardinality of B, it is also 4. Now, what about the power set of A? Power set is denoted by P of A. You have 4 elements. So the power set, if you remember, has the formula 2 power n. So n is replaced by 4. 2 power 4, there will be 16 elements. You can find the power set by yourself. So first we have to take an empty set and the set itself. Along with that, we are supposed to take the combination of all the elements of the set. Okay. Now A union B. So the next is A union B. A is equal to ABCD and B is equal to ACYZ. We are supposed to find A union B. So the solution is A, B, C, D, Y, Z. Okay, and also the Venn diagram. So for Venn diagram, you can take in this way. Okay, this is your set A. This is the universal set. This is set A, set B. To show the elements which are common, so A and C can be written over here, B, D over here, and Y, Z over here. Okay, this is the Venn diagram. Now, if you are supposed to shade it for A union B, shade the entire 2 circles. So let me do it over here. So in this way you will have to shade it, all the circles. Okay, and similarly for A intersection B, it will be AC, and similarly if you draw a Venn diagram, you are supposed to shade only the intersection. What will be A minus B? A minus B is ABCD minus ACYZ. So over here we have the common elements, cancel it. Whatever elements are left in A, those are the element, that is the solution of A minus B, which is B comma D. Okay, so I have taken an example and shown you the different set operations that we can perform, and this is the end of topic set operations. Thank you.